Hi everybody, Dr. White here with some R applications involving recent material. So I'm in RStudio, but I've got an old file that I'll close out. I've got a global environment that I would like to empty. And hey, I'll go ahead and restart my R. Always a good idea if you use RStudio for various things to restart R from time to time, so you'll know exactly what packages are loaded and not. And so right now there are no packages other than the central ones to make our work loaded. And if you do that, you're in the same place I am right now. What happens to you will be what happens to me. So I'm going to go pick up material for the current section. Let's see, common folder, white stuff, Math 331, and it's in scripts. And it's section 5.2, and I'll go ahead and save this to somewhere in my home directory. How about into my notes? So // my notes, save. Great. And while I'm at it, let me go into the files pane and just be looking back into my home folder over here in the files pane. Great. Alrighty. Betas. So the parameters for beta in the book are called alpha and beta. In R, they're called shape1 and shape2 because they both have an effect on the shape of the PDF function. Let's let X have the beta distribution where the alpha is 4 and the beta is 1. So remember how that is when you think about how betas arrived to our attention. A beta was a fraction of waiting time. When you were waiting for alpha plus beta events to occur, how much of that time was spent, what fraction of that time was spent waiting for the first alpha of the alpha plus beta events to occur. That's how you would think of it if alpha and beta were whole numbers. But of course, betas are defined also for alpha and beta's any real number. So here, this is like saying, what fraction of the time would I spend waiting for the first 4 events when I'm waiting for a total of 5? So you kind of think, Poisson process, events have the same expected time between them. So you'd expect 4/5 or 0.8. And so like the chance that it's less than or equal to 0.9 should be a pretty decent, pretty sizable chance, I would think. Let's see. So we could use the p beta member of the beta function family to find a CDF like we're looking for here. Just put in 0.9, but you got to say your shape1 and shape2 values, and off you go. And about a 65.61% chance, pretty good. You can simulate random betas if you want. Here I'm making a data frame where the only column is 10,000 random betas from this distribution. There it is. Ta-da. They're all between 0 and 1, like betas are supposed to be. And if I load up the ggplot2 package, then I could make a little density plot the usual way. And I'll have to take away my face so you can see it. But it kind of makes sense. Most of the curve is centered around here up near 0.8 or so. And so it kind of makes sense that you'd expect 80% of the waiting time to be for the first 4 of the 5 events. Hey, what might some other betas look like? Let me just sort of change this around. What if this were like shape1 is 1 and shape2 is 4? Yeah, so it's symmetrically, it's the opposite thing. I'd expect 1/5 of the time to be spent waiting for the first event out of 5. What if I'm waiting for the 4th event out of 8? What fraction of the time would I spend? It kind of makes sense. It looks like it's symmetric. Oh, I'm sorry. That would be the 4th event out of 12. So let me make it fourth event. So fourth event out of 8 would be the shape 1 and the shape 2 are both 4. Let me do that one. Yeah, that's what I was expecting to see. And so you'd kind of expect on average half the half of your time would be spent waiting for the first 4 out of 8 events. We also get kind of a bell-shaped doohickey here. What if you're waiting for like 800 events? What fraction of the time would you spend waiting for the first 400 out of the 800? Wrong. That even looks more bell-shaped. There must be something afoot here. You can explore more about the beta distribution with our little app, which I will now bring up. And I'll kill my face. And yeah, there's beta down here. So right now I've got it set where the first shape parameter is a 3 and the second one is a 1. And it looks, yeah, pretty heavily skewed towards fractions that are pretty close to 1. But if I were to bump it up a bit, yeah, so it looks like if you, so here, like, I'm waiting for the first 8 out of 9 events. And so, you know, it's pretty sure that almost all my time will be spent waiting for those first 8. Yeah. And now let me switch it around. So like have a low alpha and a higher beta, then I should get something. Yeah. And it looks like as soon as you get, like, as soon as one of your parameters is like more than 1, it looks like you could actually start to get really truly humps in the distribution. Let's see. If I move it right back to the 1, I lose my hump. Yeah, as soon as I get to the 1. What if I make both of the parameters big? I get a kind of bell shape. And in fact, that happens if the 2 parameters are the same and they both get bigger. You're getting closer and closer to a normal distribution, basically. That's sort of a theorem. Maybe not sort of, it's a theorem. Okay, enough on betas. Let me knock that out away and push the little stop sign. We did introduce the F distributions in this section, and I don't have an app, an option on the app to explore them, but why don't we at least know how to find some probabilities and some percentiles for them. So for percentiles, you would use the Q member of the family, so QF. And if I want the 90th percentile for a particular distribution, like one where the R1 is 2 and the R2 is 4, and R uses DF1 and DF2 as the names of the parameters. So that one there, that random variable is the ratio of 2 chi-squares. It's chi-square with 2 degrees of freedom divided by 2, divided by chi-square with 4 degrees of freedom divided by 4. That's the random variable. We're finding its 90th percentile, and it is equal to about 4.32. If you wanted the probability that such a random variable came out between, say, 1.2 and 4.1, then you would just subtract off 2 cumulatives like you see on line 27, at 28%. So you may have a few computational problems where you've got to find some, you know, percentiles for an F distribution. So you might need the QF, and maybe you do some probabilities, you'll probably use the PF. Okay, that's about all I have here. See you later.